Hi, welcome to Insights on the Monty Hall Problem, Part 2. In the video, The Monty Hall Problem, we introduced the brain teaser, known as the Monty Hall Problem, and gave its solution. This is the second video in a two-part series where we try to give more insight on why the solution to the Monty Hall Problem is what it is. In Insights on the Monty Hall Problem, Part 1, we saw how the problem changes if Monty doesn't know the location of the prize. In this video, we'll do two things. First, we'll revisit the Monty Hall Problem, but greatly increase the number of doors in the game, and see how this affects our intuition about the problem. And second, toward the end of this video, we'll make a few more general remarks that might shed some light on the answer to the Monty Hall Problem. This video will assume that you've already watched the video, The Monty Hall Problem, so you might want to check that out before continuing here if you haven't already. But this video is fairly independent of Part 1, so strictly speaking, you don't need that video in order to understand what we'll do here. Okay, let's get started. So let's look at the Monty Hall Problem. But this time, instead of 3 doors, let's say there are 50. Let's see what our intuition says in this case. So this time, the situation is the following. You are presented with 50 doors. Behind exactly 1 door is a prize, and the prize is equally likely to be behind each of the doors. You don't know where the prize is, but Monty does. You pick door 1. Monty doesn't open door 1. Instead, he says, let's open doors 2 through 16. Leave door 17 closed. Open doors 18 through 50. Then Monty asks you, do you want to stick with door 1 or switch to door 17? So Monty has eliminated all of the possible locations of the prize except for door 1, which you chose, and door 17. Does intuition tell you that the prize is equally likely to be behind door 1 and door 17? Or does Monty's opening of doors 1 through 16, skipping of door 17, and opening of doors 18 through 50 lead your intuition to tell you that Monty intentionally left door 17 closed for a reason? You might want to pause the video for a minute to think about what your intuition is telling you. In this case, you are much more likely to win if you switch to door 17. If you think that doors 1 and 17 are equally likely to have the prize, think about the following. You could go on the game show many times and use the following strategy. Every time you initially choose door 1. So, Monty leaves door 1 and some other door closed. Then, every time you choose not to switch to the other door. If the probabilities for the prize to be behind door 1 and the other closed door are equal, you would win half the time. But this would require the prize to be behind door 1 in half of all games. We know this is not the case, as the prize at the beginning of the game is equally likely to be behind all 50 doors. So, in our example, Monty probably left door 17 closed for a reason, namely because he knows the prize is behind door 17. Now, let's go back to the original Monty Hall problem with 3 doors. You select door 1, and Monty opens door 2. If you were to go on the show many times and always initially select door 1, sometimes Monty would open door 2 because the prize is behind door 1, and he can choose to open door 2 or door 3. But sometimes Monty opens door 2 for a reason, namely, he knows the prize is behind door 3. This skews the odds and makes it in your best interest to switch to door 3. Now, let's see if there are a few other useful things we can say about the Monty Hall problem. For all of the points below, we'll be talking about the usual formulation of the Monty Hall problem, with 3 doors. First, let's point out that the logic used above to show that the probabilities cannot be the same for door 1 and door 17 can also be used in the usual 3-door formulation of the Monty Hall problem. In the usual formulation, you choose door 1 and Monty opens door 2, revealing no prize there. Then the question is whether you should stick with door 1 or switch to door 3. While it may seem that the probabilities for the prize to be behind doors 1 and 3 would both be 1/2, this cannot be the case for the following reason. You could go on the game show many times, always pick door 1, and always refuse to switch. If the probability for the prize to be behind door 1 is 1/2, then you would win in half of your appearances on the show. But this would require the prize to be behind door 1 in half of all of the times you play. We know this is not the case because at the beginning of the game, the prize is equally likely to be behind any of the 3 doors. Okay, next, let's think about what information Monty actually gives you when he opens door 2. Let's imagine that you're about to go on the program for the first time. You have decided in advance that you'll initially choose door 1. You also have watched the show many times, and you know that Monty always can and will open one of the unchosen doors and reveal no prize. You don't know whether he'll open door 2 or door 3, but you know he'll open one of them and that there will be no prize revealed. So you go on the show and choose door 1. At this point, you know that you have a 1 in 3 chance of having chosen the correct door. But new information can change these odds. Now, before Monty opens a door, ask yourself the following. He might open door 2 or door 3. Do your odds depend on which one he opens? So, no, which door he opens can't affect your odds. The game is set up such that it treats doors 2 and 3 equally, so it doesn't matter which door he opens. Okay, so then Monty opens door 2 and shows you that there was no prize behind door 2. What information have you gained, and how does it change the odds of door 1 containing the prize? You already knew, before the show started, that he would open a door and reveal no prize. Which door he opens doesn't change the odds of door 1 containing the prize. So you've received no information which changes the odds that door 1 contains the prize. At the beginning of the show, the probability was 1 in 3 that the prize is behind door 1. You have no new information which changes those odds. So the probability that the prize is behind door 1 must still be 1 in 3. Note that if the game were different, such that Monty opened a door randomly and sometimes revealed a prize, then his opening of door 2 and showing no prize behind it would give you new information. This is because you would not know ahead of time that that result would occur. In a case like this, the odds of door 1 containing the prize do change when you get new information. Okay, so let's summarize. In this video, we've tried to explore the solution of the Monty Hall problem in more detail. We saw that our intuition about the problem may be changed in the case that the number of doors in the problem is greatly increased. If you'd like to learn more about the Monty Hall problem, and if you haven't watched it yet, you might want to check out Insights on the Monty Hall Problem, Part 1, for another perspective.